i.e. algebraically. So just a bit of terminology here. So this function on the left here is a continuous function. You're going to hear this term a lot in this class. It means you can draw the function essentially without lifting your pen off or pencil off the paper. All right, there's no undefined points. So a continuous function has no undefined points. Sometimes it's called a well-behaved function. And these are easy to solve the limits for because you just substitute in because there's no undefined points. And that's what we did with the questions at the beginning of class. Even though there was some undefined points, you can just plug the numbers in. They're the easiest ones to solve for. But they're the kind of boring ones. Right? The graph on the right is more interesting. But with that, it comes other problems. So this is not a continuous function. So you need to use, I don't want to call them tricks, I'll just say other techniques to solve the limits. Let's say methods. I like methods. You can't just use substitution to solve them. There's 3 basic types that you're going to see. Okay? And you need to know how to solve these 3 types. You will see the 3 types on a test or a quiz. They're all standard first-year calc questions. So we're just going to go through 3 of these 3 examples. So the limit so we have the limit of a rational function, which basically means a polynomial over a polynomial. It has an undefined point at what number? -3, right? Because if you put -3 in the denominator, you get 0. What is our limit going to? -3. So we can't substitute it in. Okay? We don't have a graph. Right? We'll learn how to sketch these things later. So what do we do? If you don't know what to do in this class, and it's a polynomial, factor. So what is the top factor to? You say x minus 3?
X plus 3.
Yes. So we can rewrite this as the limit as x goes to -3. The top factor is to x plus 3, x minus 2 over x plus 3. Then what happens? The x plus 3's disappear, they cancel out. And now we get the limit as x goes to -3 of x minus 2. What type of graph is that? That's just a what am I trying to say? Linear line. All right, it's a linear equation, mx plus b. But more importantly, there's no undefined points. We've removed what we call the discontinuity. Okay, this x plus 3, which goes to 0 and -3, that's called a discontinuity. It would be a hole in the graph. Okay, but because we factored it, canceled it out, that is now gone. So I can just plug in my -3 at this point. Once you do that, you can just plug it in. So the limit is -3 minus 2, which is -5. Okay, so if you have a polynomial or a rational function, factor. Sometimes you have to factor the top and the bottom, but factor everything, cancel out the factors. Okay? Second type. Is when you have a radical, specifically a square root is what you'll see in Math 100. So, first of all, you always try to plug in. Can you put x is equal to 0 in here? No, it's going to blow up because you got the x on the bottom. So you need that x to go away, okay, to disappear. If you have a square root, 99% of the time, aka for Math 100, all the time when you're doing a limit, you're going to multiply by the conjugate. Does anybody remember what a conjugate is? Okay, so if you do this, if I have x plus 1, the conjugate of x plus 1 is x minus 1. Everything's the same, you just change the sign. Now, what is this? In factoring, what would we call this? There's a specific name. Somebody said it. It's a difference of squares, right? Because when you multiply this together, you're going to get x squared minus 1. Okay? What you want to do when you multiply by the conjugate here, you want to create a difference of squares. Okay? Because you're squaring the first term. If you square a square root, what happens to the square root? Goes away, right? So the conjugate of this is root x plus 1 with the plus 1. It has to be opposite sign. Okay? But you can't just multiply the top, right? Because that's going to throw everything off. But what number can you always multiply by that never changes anything? 1. How do I make the blue part actual 1? Just a hidden one. Yeah, make it the same on the top and the bottom, right? So, because anything divided by itself is 1. So now we're just multiplying by 1. It looks weird, but it's still 1. So the top, the limit as x goes to 0. So remember, you're multiplying root x plus 1 times root x plus 1, which is just root x plus 1 all squared, which is x plus 1. What's inside? So x plus 1. Negative 1 times positive 1 is? Negative 1. Don't multiply out the bottom. Okay, just write it as now. Why don't I want you to multiply out the bottom? I mean, you can if you really want to, but we want to cancel this factor here. So we simplify the top. What does the top simplify to? It's going to be x, right? Because 1 minus 1 is 0. So what happens to the x's? They go away, which means we've removed our discontinuity. If you cancel everything up top, there's a 1 left over. So now you have now. Can I put 0 into this? You can. So you get 1 over, which is just 1/2. Okay? So whenever you see a radical, whether it's on the numerator or the denominator, rationalize it, i.e. multiply by the conjugate, top and bottom. It'll turn into a difference to squares. If you do everything right, because these questions are all rigged, your discontinuity should disappear. Okay? All right, the last kind of the sort of 3 first-year limits problems are fractionals or fractions. One over x plus 2 minus 1/2 over x. What do you always try to do first? Well, plug-in is always your first option, but you can't do that. Then you'd look at it. Could you factor this? You can't factor it. It's not really a polynomial. So if, and there's no square root, so you can't do that. So your last option when you see fractions, if you have 2 fractions, put them together. You need a common denominator. What's the common denominator for the top? Don't worry about the bottom right now. Just multiply the bottoms together. All right? That's all you do is just put the bottoms together. So essentially, this one gets multiplied by x plus 2, and this one gets multiplied by 2 and 2. The shortcut cheater method is to just bring that 2 up there, that 2 up there, and put the bottoms together. Okay, so you get the limit as x goes to 0 of 2 minus x plus 2 all over which looks worse. All right? It will look worse at first, but then it'll clean up. So the very top one, this, you have to simplify. So this negative drops into there. So I'm getting the limit of 2 minus x minus 2. What happens on the top? 2's go away, right? So I get negative x over 2. Don't multiply the bottom bit here. So I get that, which still looks worse. But you're all fraction experts. How do you divide fractions? You flip the bottom one and multiply, right? The bottom one is this x over 1. Nobody writes the 1 though. So if you flip that, so what happens to the x's? They will cancel, right? That, and you're left with negative 1 over 2 x plus 2. Can I plug 0 into that? You can, because you removed the discontinuity. If I put 0 in there, I get 0 plus 2 is 2 times 2 is 4, so I get negative 1/4. Okay? So 3 types. One, polynomials. First one here. A rational function, whatever you want to call it. Basically factor. Cancel out the factors. Second type, you're going to have a radical. You rationalize it by multiplying by the conjugate. Okay, it turns into a difference of squares. Third type is a fractional one. Put the fraction together by making a common denominator and then simplify. They're all rigged to work. All right, because we're just starting calculus. So within 1 to 2 steps, you should see stuff that, oh yeah, okay, it's going to cancel. All right. If it doesn't, you've either made an algebra mistake or you've done something weird right at the beginning. Okay, so that's your hint. Are there any questions about that? We're good? All right, here's your practice, peoples. Page 67, numbers 41, 43, 47, 49. And then 51 to 57. I don't know why I just didn't write 47 to 57 odd, but whatever. These are all just odd. And then we're going to start trig. Everybody's favorite. Okay. So b is a constant. If you have a constant in your limit, you can pull constants outside. So you can rewrite it as b times the limit as x goes to c of your function. So what would that look like? A simple example would be this. Okay, this is an ultra simple example. You wouldn't have to just do this, but you can pull the constant 3 out of this. And you get the same answer. Okay? So sometimes it is valuable to pull a constant inside and outside of the limit. If it's that simple, you don't really need to, but it is possible. Second one, we will use. If you have two functions that are being added or subtracted together, you can break up the limit into the limit of the first one plus minus the limit of the second one. And I'm going to show you an example of this in a bit. So if I have this function, I could, in theory, write it like this. So you can break up anything that's being added or subtracted. You can do little mini limits on those and then add the answers together at the end. Okay. The third one, you can do that for multiplication as well. So I can rewrite this as the limit as x goes to c of f of x times the limit of the other function. So simple example would be, let's use polynomials. And then if you can do it for multiplication, you can do it for division, because division is just a type of multiplication, essentially. So I can rewrite this as the limit of the top function, over the limit of the bottom function, denominator. So, just hanging out? Okay. So if you have a simple function like that, we could just plug it in, but if for some reason you wanted to, you could break it up to the limit of the top one divided by the limit of the bottom one. And the final one, if your function is raised to a power, which is the n here, you can just ignore that power. Ignore it's the wrong word, but pull it outside. So rewrite it as the limit of the inside, the simple function, f of x, whatever answer you get, then you raise it to that power. So I could go, x goes to 2 of x plus 5 all squared. I could just go, well, the x plus 5 is easier to deal with, and then raise it to the power. All right. So I'm going to show you an example where this would be useful. This is taken from a Math 100 quiz. And by quiz, I mean test. He just called them quizzes. So we'll do this one together, and then I'll give you one to practice on your own, and then we'll move on to trig limits. So here we go. We're going to do the limit as x goes to 6, 5 over 2x plus 3 minus 1/3 over, you know what we're going to do? We're going to plus x squared minus 36 all over x minus 6 minus 1, which looks like an absolute gong show. Okay? So right away, the first thing you try to do is plug in. Can you plug in? No, because you get 6, you get a 0 in the denominator and it blows up, right? So that means you have to rewrite this thing. So because we're adding and subtracting, we can break them as separate limits, but you want to be careful about how you break this up. Okay? Hopefully you see that we learned 3 techniques, right? One is factoring, one is rationalizing if you have a radical, and one is if you have fractions. Well, there are some fractions, right? So I want to make that one limit. Here's a polynomial. So I'm going to make that the other limit. And hopefully you can see right away, what is this? If I just treat it as x squared minus 36 in brackets. It's the difference of squares, which we factor to x plus 6 and x minus 6, which is going to make that disappear, right? So the first thing is when you have a denominator like this and you're being adding and subtracting, you need to break it up. So this is going to become the limit as x goes to 6 of 5 over 2x plus 3 minus 1/3. That is all divided by x minus 6. Plus the limit as x goes to 6 of x squared minus 36 over x minus 6. Because that denominator has to go to both, right? Because we're doing the reverse of combining. If I give you these two things, you've got a common denominator. Then you can put them together, which will give you this. Okay, so we're just doing the opposite. And then the -1 thing just hangs out there by itself, but it's still a limit. So it's a limit as x goes to 6 of 1. So I can pull the negative outside of the limit. Okay? Because that's the constant. That's, if you look at the rules, that's essentially this rule right here. That is essentially this rule right here. The -1 I can pull out. Okay? All right, so now we solve each one separately. Okay? So right away, well, what's this one? The last one. It's just 1, right? Because it's a horizontal line. Everybody agree with that? So then we know that's going to be 1. So that equals 1. Let's do the middle one because I think we know what to do with this one. What do we do with the middle one? You're going to factor it, right? So we get x plus 6 x minus 6's go away. So what is that limit? Just 12. So that gives me 12. Okay. And then the final one, we need to deal with the fractional one. What do we do with the fractions? Common denominator on the top, put the fractions together. So the cheater way, remember, is you just, that's your common denominator, and the 3 goes there, and the 2x plus 3 goes there. So you end up with 3 times 5, which is 15. So you get 15 minus 2x plus 3. Be careful with that. If you're multiplying this up to here, it's subtracting the whole thing. So remember to put it in brackets, because you're going to flip the signs, right? Or just remember to flip the signs. Over, and then the denominator is just 3 times 2x plus 3, and it's all over x minus 6. So now we just have to clean that up. What's 15 minus 3? 12, right? So I get 12 minus 2x over 3 times 2x plus 3 over x minus 6. Everybody with me? Yeah? Okay. What do we do now? So flip the bottom fraction. So remember the x minus 6, even if you want at the beginning, like up here, you can just do that if that helps you, right? Because the x minus 6 is the bottom fraction. So you know when you flip it, you're going to get the limit of 12 minus 2x over 2x plus 3 times 1 over x minus 6. Okay. What is the whole point of this? What usually happens at this point? This is going to go away somehow, right? It doesn't look like it's going to right now. But does anybody see how I can make this into that? factor what? Not just a 2, a negative 2, right? Because that's going to flip the signs here. So if you pull a negative 2 out of there, that flips the signs, and I get x minus 6. Then they go away. And now you can plug in x is equal to 6. So you would get negative 2 over 6 times 2 is 12, plus 3 is 15. 15 and 3 is 45. So that limit equals 45. What's the final step? Add everything together, right? So this plus this minus that. So you get negative 2 over 45 plus 12 minus 1. You do it on a calculator, or you do it on a... Yeah, just do it on a calculator. I don't care. It's about 10.95. All right. So that's about as ugly as it's going to get. All right. Because that combined 3 or 4 different things into one limit. You would only see one of those types on the test. It's mostly algebra, and that's what calculus is. If you have strong algebra skills, you will be okay. If your algebra skills aren't as strong, you're going to struggle, but I can give you questions that will help you with your algebra. So if you need help with your algebra, please come see me. All right, I'm just going to give you one more to do here, and then I'll post the answer, and then we'll move on to trig. So, what did I do with it? What did I do with it? Oh, there it is. Here's the one I want you to do. The limit as x goes to 0 that. I'm going to freeze it, and you can work on it, and then I will post the answer. That is x goes to 0, yes. You're going to have to break it up. You just have to decide how you're going to break it up. What would you want to do? No. It would be a lot easier. You just go like this? Yeah. Cannot do that. What would be the best way to break it up? Let me give you that hint. Leave it right there. All right? But they're both going to be over x. Okay? We ready? You want a couple more minutes? Couple more, go. What's x over x? 1. So its limit as x goes to 0 of 1.
Oh, okay. I was like, I don't know what to do.
All right, you ready? Either one, I don't care. Or this, or this, or this, plus what? I don't really care. If you punch in your calculator, it should be about 0.646. People get it?
Yeah.
Sweet. If you can get that, then you understand limits. Okay? Is there any questions about that? The only trick I saw some people forget, or I should say forget, but miss out, is 2 minus 2 is 0. Obviously, that goes away, but you have negative x. When you cancel the x's, you're left with a negative 1. All right, don't forget the negative. But if you have x over x, that's just 1. So the limit of 1, doesn't matter what number you're going to, is just 1. And just add that on the end. Okay? So we're all right? All right. Trig stuff. So I handed out your, yep.
What's that thing called when you have to make it equal the other side? You know, we did this in pre-calc.
Proving?
No,
Proofs?
the name. You like do the equation on both sides and you have to make it equal.
That's proof.
Oh, good. Are we gonna do those?
No.
Okay.
This is just to help us with some trig identities that I don't think anybody remembers. But there's really only a couple that we're going to use. So. Okay, so that's why I handed this out. I will give you, you don't get a cheat sheet in this class, but like I'm not, like this is about introductory calculus, just getting you used to it. So I'll give you this formula sheet for trig functions. I'm going to give you a formula sheet later on for derivatives and all this kind of stuff. I care about, can you actually do the stuff? That's my biggest thing here, okay? In university, you don't get any of this stuff. You just have to memorize it. But hopefully we'll do enough practice that you will just know it. All right, trig limits. Okay, so maybe we should make this our own page. Boom. All right, trig limits. So I'm going to give you a couple of limits that you just need to know. Okay, actually, I'll write them on the board for a test or something, but they're not too tough. So I don't want to do this in blue. No, whatever. So the two special trig limits are the limit as x goes to 0 sine x over x equals 1. You don't have to prove that. It will be given to you. You just have to know when to use it. And the other one is the limit as x goes to 0 of 1 minus cos x over x equals 0. Okay, I will provide those to you. You just need to manipulate the function to get to those points. Okay, that's what trig limits are all about. It's about manipulations. So when we did proofs in grade 12, that was sort of practice for this. We're not going to do proofs, but being able to manipulate trig functions because they have all these different trig identities. We're only going to use the basic ones. Is what makes trig tricky. Okay. So we'll start with some simple ones. So if I said the limit as x goes to 0 of sine x. So first of all, if you're going to use your calculator in this class, what mode must it be in? Radians. Okay? So if you're going to use your calculator, it has to be in rad mode. Okay? So make sure you can get your calculator in rad mode. All right. One sec. So limit is x goes to 0 of sine x. Do we remember what the sine graph looks like? Okay. I'll draw it up here. We will use this. You don't have to know it, but I find it does help. And that would be 2 pi. And that would be pi. Okay. That's a sine graph. Is it continuous? Does it have any undefined points in it? No, it does not. So if you're solving a limit with sine like that, what's the easiest thing you do? You just plug it in. Okay? So you just plug it in. Sine of 0, which is, if you look at the graph or you put it in your calculator, 0. That's it. If you can plug it in, plug it in. All right? So the limit as x goes to 0 of sine x over 2x. Now this looks like the one up top, right? Our special one. But it's not identical. What's wrong with it? It's got a 2x in the bottom. But remember our limit rules. What are we allowed to do with constants? You can pull them outside the limit. So I can rewrite this as 1/2 the limit as x goes to 0 of sine x over x. Now, we've made our limit look like the one up there. What is the limit of sine x over x as x goes to 0? It's 1, right? So this just becomes 1/2 times 1, which is just 1/2. Is that okay? All right. Sine 4x over x. What does that look like? Or what is it close to anyway? It's close to the sine one on the left at the top there in the blue. But what's wrong with it? Got this stupid 4x in there. Now, you cannot take the 4 out, okay? Because it's inside the trig function. So you cannot touch anything that is in here, inside a trig function, you can't take it out. Unless you're going to use a different identity, but we don't know. We're not doing that. Okay? You can't pull the 4 out like you did here where you pulled the 1/2 out. But what we can do is if I had a 4 there, all that matters is that these two things, what's in here and what's in the bottom, match. Okay? If they match, the limit is 1. Okay? So I can put a 4 there as long as I do what? You have to have a 4 up top, because what number can you always multiply by without changing anything? 1. So instead of writing a 4 on the bottom, if I write it like that, 4 divided by 4 is 1. So I'm really just multiplying by 1. And then using the constant rule, what can I do with the 4 in the top? You can pull it out. So I can write it like, whoops, 4 should be out there. And I get sine 4x over 4x. Now, this is what? It's 1. It's essentially the top there. Okay? So I get 4 times 1, which is 4. We okay? All right. Do another one of these sine, a couple more of these sine ones. So that's a sine of t minus 3 over t minus 3 as t goes to 3. So you can't punch it in because you'll end up with 0 in the denominator. But it's sort of, not quite, sort of looks like this one. But not quite. Okay? So I have to make it look like that. So what we're going to do is we're going to do a substitution. We're going to go u is equal to t minus 3. Okay. So that would give us a limit of sine u over u. Does everybody agree with that? Okay. But what are we approaching? If u is equal to t minus 3 and t is going to 3, what is u approaching? 0, right? Because I can put this 3 into there. So therefore, u is going to 0, right? If I put this, I put this 3 into there, I get u is going to 0. So that means my limit is u goes to 0, which matches this. The variables are different, but that's irrelevant. Okay? This is exactly the same as this. So what's my answer? It's 1. When you're doing trig functions, you always want to make them look like that up there. All right, I got one more sine one, then we'll move to some other stuff. Limit as x goes to 0 of x over sine x. Does that look like the blue one? It sort of does, but what's wrong with it? It's flipped. How do I flip it back? Make the exponent negative. Make it all to the negative 1. So I can rewrite it as that's the same thing, right? Because a negative exponent means you flip it. What did I say about if you have a power in the properties? Oh, it's on another page. To the bottom here. Right here, this bottom one. If you have something, a function to an exponent, I can do the limit of the inside function and raise my answer to that exponent. So, so that's what I can do here, is I can go the limit as x goes to 0 of sine x over x to the negative 1. The whole thing. So what's the limit as x goes to 0 of sine x over x? 1. What's 1 to the negative 1? 1. Okay? Because this is just means 1 to the negative 1 like that, which is like 1 over 1 to the power of 1. All right, the negative exponent just flips it. So we can actually add that to the top, the blue bit. I'll just add a third one, or it's not really a third one, but basically you can also, you don't have to write this if you don't want to, you can just remember it. The limit as x goes to 0 of x over sine of x is equal to 1 as well. So these two are just reciprocals of each other, but it's accepted. So if you get something like this in your limit, you can just write 1. You don't have to go through what I just did. All right, just a few more to do, and then I will unleash you on the textbook. All right. what if we have done a lot of sine ones? Let's do a cosine one. Limit as x goes to pi over 4. Okay, so we have a tan. First of all, what is pi over 4? 45 degrees. So if you do sine of 45 and cosine of 45, because you always want to try plugging it in, all right? They're actually the same answer. So if you subtract them, the bottom can turn into 0. So you can't do it, all right? We have not talked about tan. If you have tan in your equation, just like you did in math 12, you need to get rid of it. How do you rewrite tan in terms of sine and cosine? Sine over cosine. And it's top right corner of that sheet I just gave you. All right? So tan is actually sine over cosine. Now, what does this look like? I know it's got all the trig functions in it, but if it was numbers, what does it remind us that we just did? What are the 3 types of limits that we were looking at? It's the fraction one, right? What do you do if you have a fraction one? Common denominator? Is that what you said? No? You get a common denominator. Okay? Just like when we did, like if you had 1/2 minus 1 over 2x plus 3. Common denominator. What's the common denominator of this function here? Cosine. It's just this. So this, so you're going to get, I'll write it out in step by step. So all I did is this one, I multiplied top and bottom by cosine. Now you put them together, and I'll get which looks horrendous. What do we do when we have fraction over fraction? Flip. So we get one over. This is going to be the trickiest one you would ever get, okay? Okay, what are we trying to do? Trying to cancel those, right? How can I make them look like each other? If you factor a negative out of here, that'll flip all the signs. So if you go -1, and you'll get then they cancel. And I forgot to write limit all the way through. So it's the limit as x goes to pi over 4, or 45, of negative 1 over cos of x. And if you punch that in your calculator, you should get negative root 2, which is about negative 1.41 bunch of stuff. Okay? That's as bad as it would get. I'll show you what I would expect you to do on a test. It'll be a little easier than that. Okay? These can get crazy, right? We can just make the functions insane. Okay? I'm not going to do that. Here's one that I would expect that you could do, though. If I gave you this, limit as x goes to 0 of tan x over x, or something similar to this. Obviously, we can't put in 0, because we'd be dividing by 0. What is tan? Sine over cosine. So we would rewrite it all over x. And then using our skills that we've learned, if you have fraction over fraction, you flip and multiply. So we would get that. And then we pick apart this to make it look like one of our special integrals, or special limits, sorry. Okay? So because it's being multiplied, you can do it any way you want. But hopefully you can see that if I take that, right, that's sine x over x. That's our special limit. So I can rewrite this as the limit as x goes to 0, sine x over x times limit as x goes to 0 of cos x. All right, so all I did is I took this, and because they're being multiplied, I can multiply the individual limits of it. All right, sine x over x is what? 1. If you put 0 into cosine, put cos of 0 in your calculator. 1 times 1 is 1. You gotta throw it in. So it's 1. Okay. All right. Practice questions. I think I've melted your brain enough today. So page 67, 63 to 73 odd, 75 to 81 odd, please. So really to 63 to 81 odd. That would have been a better way of saying that.